Alright there, AP Chem Scholars. Welcome to Unit 2. In Unit 2, as you can see, we're getting into molecular and ionic compound structures and properties. Today, though, we're only going to talk about types of bonds. Come on, work with me. There it is. Types of bonds. Okay. So, we are going to discuss 4 categories of bonds. Nonpolar covalent, polar covalent, ionic, and metallic. As far as the first 3 goes, it really comes down to the idea of electronegativity. Okay, you know that electronegativity from left to right increases, from top to bottom it decreases. Okay, when we're talking about nonpolar covalent bonds, we're assuming that the 2 atoms involved in this bond have nearly identical electronegativities. Okay? Neither one can pull harder than the other one, forcing them to share electrons equally. So, for example, if I were to talk about a hydrogen-hydrogen bond, an oxygen-oxygen bond, obviously the hydrogen-hydrogen, both of them are the same thing. Neither one should pull harder. Same thing with the oxygen-oxygen. And I threw in carbon and selenium because you notice that they're both listed at 2.55. So the difference, even if there is one, is pretty minimal. That would be considered a nonpolar covalent bond. Sometimes people throw out specific numbers, like if the difference between them is 0.05 or less. Let's not worry about that. We're just going to say nonpolar, they got to be pretty much identical electronegativities. Okay? What does that mean? Okay? What's going on there is, again, you have 2 atoms that are pretty much the same, and they come together, they start to overlap. The nuclei are each pulling on the same shared electrons, and that is what the covalent bond is. After all, co means together or share or with, and valent, valence electrons. So we're talking about sharing valence electrons in a covalent bond. Okay, so really no big deal there. At the other end of the spectrum would be ionic bonds. Now we're going to throw out a number just for reference sake, but really, again, we just want things that are very different in electronegativity. Okay, so I'm going to, reference this number 1.7 briefly here and never again in this class. Okay, if we take things that are really high in electronegativity and things that are really low in electronegativity, then it is very ionic. Okay, so sometimes we talk about percent ionic character, blah, blah, blah. That hasn't been on the AP exam in years, so not going to talk about it. But in any event, we want things that are very, very different so that if I put fluorine and francium together, for example, fluorine being so strong and francium being so weak, there's no contest. That electron is not going to be shared because fluorine's saying, yoink, it's mine, you're done. And francium's like, whatever. So the reaction would be almost explosive just because of the fact that they are so different. So, again, sodium chloride, barium oxide, potassium iodide, things that we normally think are ionic, although a few actually fall in the middle category that we're going to talk about in a moment. Now, again, we mentioned ionic bonds in Unit 1, so this is really just a brief review. We're talking about a transfer of electrons when we're making an ionic bond. So the sodium atom doesn't really want its valence electron. Chlorine very much wants another one. So that electron gets transferred, making a cation and an anion that electrically attract. Okay. Now I made it sound like sodium's giving it, but it's more along the line of chlorine is taking it because chlorine is that much stronger in terms of electronegativity. All right, so now to the middle ground, the polar covalent. So if they're almost identical electronegativities, we say it is nonpolar. If it's pretty far apart, we say it is ionic. And so there's a gray area in between where it's different, but not different enough to be ionic. Now, technically, we could extend this to metals and non-metal combinations. For example, if I put aluminum and silicon together, the difference is there, but it's not huge. But again, we will talk about polar covalent generally just in terms of non-metal to non-metal. Okay, so if I put carbon with an oxygen, again, oxygen is a bit stronger, but not strong enough to take from carbon. If we put phosphorus and chlorine together, again, chlorine is stronger, but not enough to take the electron away, and so on. And you'll notice that I even included xenon in this, okay, xenon and fluorine, just to emphasize the fact that, xenon can form bonds, and we will see it here and there in the course. And technically, krypton does under some extent, and radon would as well. This is an older table, but radon's radioactive, so again, really it doesn't matter. So, what's going on there? Well, again, we're getting the same idea. It's just that when it's polar covalent, one of the atoms, being much stronger, is taking the electron a little bit more towards it. Okay, so it's kind of like, you got a pizza and you're going to share it with your friends, and you take 6 slices, they take 2. Okay, you're sharing, but not sharing equally. The electrons are being pulled much more towards fluorine, but not, again, not enough to the fact that hydrogen can't hold on to it at all. Okay. All right, so most of the times we just talk about 3 types of bonds, okay, the nonpolar covalent, the polar covalent, and ionic. But we do have to talk about a 4th class of bonds, metallic bonds. Okay, metallic bonds are bonds between metals. Wow. Metals tend to delocalize their valence electrons. I think we used that term before. Metals have very loose valence electrons, and so those electrons can kind of like almost float off. Sometimes they use the term a sea of electrons, that the metal cations are floating around it. Okay, but in any event, when we talk about a metallic bond, it's just a metal to a metal, and it's somewhere in between covalent and ionic. When these electrons delocalize, the atoms become cations. So this positive would represent, let's say, an aluminum atom without 3 of its valence electrons that just left and are going wandering. The difference, though, here is that we don't have anions. We have cations, and then we have electrons. But you see the electrons just kind of all around, and the cations are swimming in that sea of electrons. So it's, in a way, covalent in that we're talking about attractions to the electrons between different nuclei, but it's also kind of ionic in the fact that we're talking about cations being attracted to these negative particles. So it's a little bit of a unique situation there. So those are your basic bond types. Give the questions a try. Let me know if you have questions. And this PowerPoint is posted in with the notes, so you could always look at it when you need to. Ciao for now.